Here we have the cathode ray tube. This was an important experiment in physics. It was one of the four great experiments, the four great papers that Einstein wrote about, which led to classical physics being replaced with quantum mechanics. And in that experiment, they realized that you could shine the brightest of red lights on this metal plate and nothing would happen. But the faintest and dimmest of blue lights would cause an electron to get ejected and fly across the vacuum and hit the other metal plate. And that didn't make sense in classical physics because a brighter light has more energy. And so how could something that's weak energy outperform something that's strong energy? It wasn't until they developed quantum mechanics that they realized that what actually mattered was the individual energy of each photon. And if the individual photons didn't have the threshold necessary energy to eject an electron, it didn't matter how many you had of them. You could have the brightest red light with the most photons, and it made no difference because each of those photons did not have enough energy, so it didn't matter how many you had. Whereas one blue photon had enough energy to dislodge an electron, and so it only required one photon. And so that was one of the major experiments that led classical physics to become quantum mechanics. Another good question was, if the nucleus is positive and electrons are negative, why don't the electrons just get sucked up into the nucleus? Why do they keep spinning around perpetually? And that wasn't answered until we realized that electrons were not particles. Electrons are only half particle-like, but they're also half wave-like, and it's actually the wave properties of the electron which explain why they don't get sucked up by the nucleus. So here, we have a cathode ray. If you grew up in a house that had a gigantic TV that was a couple feet deep, it had one of these inside of it. Those old school televisions had an electron gun which would shoot electrons at a phosphorescent screen and make it light up, and that gave you the image of your television. And that's also why back in those days, you were told not to sit too close to the television, because there was actually beta radiation coming out of it. There were electrons piercing through the glass screen of the television, which could get someone if they were sitting too close to it. These days, with flat screens, that's LCDs, liquid crystal displays, backlit by LEDs, and you don't have that worry. There's no electron gun whatsoever anymore. So that technology has been obsoleted. All right, so here, an electron beam is deflected by both electric and magnetic fields, indicating that it has charge. And electricity and magnetism are two different manifestations of the same force, which is why we typically call it the electromagnetic force. Because with magnets, you can make electricity, like at a power plant. And with electricity, you can make magnetism, like an electromagnet. And so they can both easily be converted into each other because they're the same fundamental force. Electrons are a particle with a negative charge of -1. That's a relative charge. The relative charge is -1. And they have an extremely small mass, 9.11 times 10 to the 28th grams, and they're super tiny. Protons and neutrons are actually 1,837 times bigger than electrons. Again, electrons are fundamental. We do not think an electron can be broken down into anything more simple whatsoever. Whereas protons and neutrons are not fundamental particles. Each protons are made up of 3 quarks that are bound together by the nuclear strong force. And neutrons are made up of 3 quarks bound together by the nuclear strong force. So protons and neutrons are made up of even simpler particles, whereas electrons are fundamental particles to the best of our knowledge and cannot be broken down into anything simpler, which is why they're so much smaller than protons and neutrons. Thomson came up with the plum pudding model of the atom, in which there were a positively charged sphere with electrons, kind of randomly distributed, like plums are in a plum pudding. And back in England, plums were kind of slang for any fruit that got put into a plum pudding, which has no direct equivalent in America, but I guess I would say it's more like a fruit cake, because it's a bread-type food, but it's a dessert, and there are fruits distributed throughout it. And that's one of the differences between British English and American English, the way they use the word pudding. So if you look up like a Yorkshire pudding, it looks more like a bread, like something you might get at Dunkin' Donuts. Whereas when an American says pudding, they mean a thick milk-based liquid, like chocolate pudding in a bowl, that's very thick. And so very different uses of that word, actually, between British English and American English. And so this was the British version of it, the plum pudding model of the atom, in which the electrons were just randomly scattered throughout like raisins might be in a dessert bread. Note, the neutron had not yet been discovered. So once the electron was discovered, they found a negative charge. It made intuitive sense that there had to be a positively charged particle out there balancing out the negatives. And thus the proton was discovered pretty soon after. But it took about 50 more years to discover the neutron. So to make cations, you lose electrons. To make anions, you gain electrons. In chemistry, we don't mess with the nucleus. Metals form cations by giving up electrons. Nonmetals form anions by gaining electrons, but ion formation always deals with either gaining or losing electrons. Neutrons, again, as we said, were discovered in 1932. During this time period, there was a big push in nuclear research. The Nazi regime in Germany was pushing hard to make nuclear energy and a nuclear weapon, and so America wanted to get there first. And so a lot of energy went into nuclear research. And what happened was the research was advanced enough that they realized a nucleus wouldn't be stable with just protons in the nucleus, because the positive and positives, they would repel each other so much that the nuclear strong force wouldn't be strong enough to hold them together. So they realized there had to be another particle in there acting like a glue to hold the nucleus together. And when they went back to the nucleus looking for another particle, and again, they knew the nucleus was positive and the proton was positive, so now for the first time, the idea of a neutral particle was entertained. And looking at the nucleus, they then did discover the neutron, and then that made the mathematical quantum mechanics work. And they realized that with neutrons and protons in the nucleus, you do form stable nucleuses. And if we ever look at chapter 18, we don't in this class, but in Chemistry 2, we cover Chapter 18, which is the nuclear chemistry portion of it. And you see that nucleuses are most stable when they have a 1-to-1 ratio of protons and neutrons. And if you veer too much away from that, that's when you get unstable isotopes, which are radioactive. So neutrons, just like a proton, it is made up of 3 quarks. It has no charge, and it has a very similar mass to that of a proton. If we look at the specifics, a neutron is just a little bit heavier. It's 1.675 times 10 to the negative 24ths, as opposed to 1.673. So it's within 1% the same mass, just a very, very, very slight different mass. And with relative masses, we just consider both of them one atomic mass unit. So electrons are -1, protons are +1. Neutrons are 0. The chemical properties of atoms can be described based on their electrons, protons, and neutrons. Though other subatomic particles are now known, the theory of the atomic structure is based on these 3 subatomic particles, and this is where we leave it in chemistry. Going into any more depth into particles is nuclear physics and particle physics, and not chemistry anymore. In general, chemistry is the science of electrons, gaining electrons, losing electrons, sharing electrons, electrons of one chemical interacting with the electrons of another chemical. So electrons are the key player in chemistry. We never mess with the nucleus in chemistry in this class. In 1911, Ernest Rutherford established the nuclear model of the atom by bombarding gold atoms with alpha particles. And he chose gold because gold is an extremely soft metal that is extremely malleable. And so even with the technology of 1911, a goldsmith with his hammers could pound gold into gold leaf, which is super thin. It's about 80 to 100 atoms thick. And that was the absolute thinnest metal sample that was possible back in those days, and that's why he chose gold foil. He wanted to probe the structure of the atoms. And so again, in theory, just a single atom deep would have been the best, but that wasn't possible back then with the technology that was available in his time. And so he found a source of alpha radiation, And he set up an apparatus to shoot alpha particles at the gold foil. And what he found was that most of them traveled right through as if they had traveled through empty space. Some of them deflected as if they'd gotten close to something of like charge, and because an alpha particle is positive, each alpha particle is +2 in charge. It's basically a helium nucleus. Therefore, it came close to something else that was positively charged in the atom. And then they also saw a very small amount of particles actually got deflected backwards. And from a physics perspective, that means they smashed into something much bigger than them and actually bounced them backwards. So if you're driving your car and you run over a mailbox, you'll just run it over. It's not going to bounce your car backwards. But if you're driving your car and you run into a building, that might bounce your car backwards. If you hit something much, much, much more massive, then the momentum can be reversed and an object can bounce off of it. And that's exactly what happened here. And so Rutherford realized that whatever his alpha particles had hit were a lot bigger than the alpha particle. And he came up with the theory of the nucleus, that all the protons were in the center. Again, this is 1911. We just saw neutrons are not discovered until 1932. So in his theory, it's just protons in the middle. Later, they realized it was protons and neutrons in the nucleus. And the nucleus is tiny. The atom is 100,000 times bigger than the nucleus. So the atom is 100,000 times longer across than the nucleus is. And so if the atom is a football stadium, the nucleus would be a golf ball at center field. So the nucleus is extremely tiny. It takes up a very, very, very tiny amount of the space of the atom, and yet all the mass is there. And so while it's only taking up 0.0000001% of the space, all the mass is concentrated in the nucleus, and the electronic orbitals flow around it. The atomic number. This is the number of protons in the nucleus of an atom. And the atomic number determines the identity of the atom. Because the neutron number can vary, like carbon-12, carbon-13, and carbon-14 all have different number of neutrons. And so the neutron number can change with the identity, or can change with the atom, and so with the isotope. And so they're all carbon. Carbon-12, carbon-13, and carbon-14 are all carbon, but they have different number of neutrons. And elements can gain and lose electrons. They're still the same element, but they have different number of electrons because they've gained electrons or lost electrons to form positive and negative charges. But if you change the number of protons, you change the atom itself. And so carbon has to have 6 protons. If you don't have 6 protons, you don't have carbon. If you don't have 5 protons, you don't have boron. If you don't have 3 protons, you don't have lithium. If you change the protons, you change the element. And that's not true with the neutrons or the electrons. You can have the same element and just have different charges with different electrons or different isotopes with different neutrons, but it's the same element. But you can never change protons because that does change the element. So as the proton is the only subatomic particle that's not varying at any point, we base our periodic table on the atomic number. So the atomic number is above the symbol for the element. So cobalt is number 27. It has 27 protons. After the discovery of the nuclear model of the atom, the mass of almost all atoms were found to be larger than expected. And again, we discovered neutrons while we were probing the nucleus in an effort to make nuclear bombs and produce nuclear energy during this time frame. Though all atoms of the same element have the same number of protons, again, they can have different number of neutrons if they're a different isotope, like hydrogen-1, hydrogen-2, and hydrogen-3, protium, deuterium, and tritium. Protium has no neutrons, deuterium has 1 neutron, tritium has 2 neutrons in the nucleus. So isotopes are atoms of an element with the same number of protons, but different number of neutrons. So again, here we see our 3 isotopes of hydrogen. Hydrogen is the only element that the isotopes actually get names For all the other elements, they just get a number, like nitrogen 14, nitrogen 15, oxygen 16, oxygen 17, oxygen 18, carbon 12, carbon 13, carbon 14. You just say the name of the element and then the mass number, which is both the protons plus the neutrons. And here we see the notation. You have the elemental symbol, which is the 1 or 2 letter symbol from the periodic table. The upper left is the mass number. That's protons and neutrons, because that's where all the mass is, and the protons and the neutrons. And then the lower left is the atomic number. That's just protons. And protons, the mass number minus the atomic number gives you the number of neutrons, because the mass number is protons plus neutrons. So if we minus protons from the protons and neutrons, that just gives us neutrons, which is what we see here. So how many protons, neutrons, and electrons are found in each of the following isotopes? Well, we look at the lower left, and it's got 29 protons. And we see no charge. There's no plus or minus, so it's a neutral element. Therefore, if there's 29 positive protons, there's got to be 29 negative electrons. And then to find the mass number, we take 64 minus 29 to get 35 neutrons. So 29 protons, since there's no charge, it's also 29 electrons. And then we take the mass number minus the atomic number to get 35 neutrons.